Hi there. Yesterday I asked you a question related to the current carrying conductors and the force experienced by these conductors due to their magnetic fields. Now the question was that two long parallel wires are placed 5 centimeter apart in vacuum. You have two current carrying conductors and they are placed at a distance of 5 centimeters with respect to each other, right? Wire A, the first wire is labeled as wire A. It carries a steady current of 10 amperes upward. The current flowing in first wire is directed in upward direction. Whereas the second wire, which is labeled as wire B, the current flowing through this wire is 15 amperes, but it is directed in downward direction. Right? You got my point? There are two wires, current carrying conductors, and they are placed at 5 centimeters distance with respect to each other. Current flowing through first wire is directed in upward direction and its magnitude is 10 amperes, whereas the second current is flowing in downward direction and its magnitude is 15 amperes. Now the question was that what is the force per unit length between the wires at 5 centimeters and 10 centimeters. You have to determine the force experienced by these wires per unit their respective lengths at 5 centimeter distance when they are 5 centimeters apart, and then when they are 10 centimeters apart. You have to calculate the force per unit length at two different distances. The second question is that what is the total mechanical work done per unit length in increasing the separation from 5 centimeters to 10 centimeter. Here in this case, you have to calculate the work done per unit length. When the separation between the wires is increased from 5 centimeters to 10 centimeters. You can observe it visually here in this figure, in these two figures. In the first figure, the separation between the conductors is 5 centimeter, whereas in the second figure, the separation is increased to 10 centimeters. Here in this case, current is flowing in upward direction in the first wire, 10 amperes is its magnitude, whereas in the second wire, 15 ampere current is flowing in downward direction. As the two currents are flowing in opposite direction, so there will exist a force of repulsion between them. You know that we have already derived this relation in our previous lecture, that whenever the current flowing in upward direction or downward direction, or we can say that when the current direction in both the wires is same, then there will exist a force of attraction between the wires. But if the direction of currents is reversed, or the direction of currents are opposite with respect to each other, then there will exist a force of repulsion between the wires. So here again, the distance is increased to 10 centimeters and you have to calculate the force per unit length for both the cases. Now let's solve the first question. You know that the relation for force per unit length that we have already derived in our previous video, it is mu naught I1 I2 over 2 pi r, where mu naught is the constant of permeability of free space and its value is 4 pi into 10 raised to power minus 7 Newton per ampere square. Other units used for it are Henry per meter or Tesla meter per ampere. So you just have to put the values, all the values are given to you, just have to put the values in this equation and you will get the answer for force per unit length at 5 centimeter distance. You will convert the 5 centimeter distance into meters, 0.05 meters. So just putting the values, you will get 6 into 10 raised to power minus 4 Newton per meter, the value for force per unit length. But the nature of this force will be repulsive. Similarly, using the other distance 10 centimeters, converting it into meters, it will give you 0.01 meters. Just putting the values for force per unit length, you will get the value 3 into 10 raised to power minus 4 Newton per meter at 10 centimeter distance between the wires. So you got my point. Now the second question is that you have to calculate the work done per unit length. You know that work is expressed as force into distance. So here in this case, you have to calculate the work per unit length. So you will integrate the equation for work over distance because distance is changed. So you will integrate this equation over F dot dr. Just put the values for the equation for force. You have the equation for force as mu naught I1 I2 over 2 pi r. We will keep r inside the integral. We'll integrate it over distance 1 over r dr. So solving it, you will get integral of 1 over r is equal to log of r, and the integral, it varies from r1 to r2. So just solve it, you will get log of r2 minus log of r1, which can be written as log of r2 over r1. So the force per unit length equation that we have derived for work per unit length is mu naught I1 I2 over 2 pi into log of r2 over r1. Just putting the values, you will get the equation result for work per unit length as 2.08 into 10 raised to power minus 5 joules per meters. So you got my point? Now the third question is that where does this energy come from, given that magnetic forces are often said to do no work? So the magnetic force appear to do no work because it is perpendicular to the moving charges. Yet here mechanical work is clearly done. So where does this energy come from? It comes from the power sources maintaining the currents. As the wires move apart, the system's magnetic energy changes and the external circuit quietly supplies that energy. So you got my point? It was a simple numerical problem, and let's see you in the next video with another point to discuss.